Hello, everyone. Welcome to OT Insights. I'm Ed Rojas. In the last episodes, we spoke about artificial intelligence with Marisa Morales Rodriguez. If you haven't watched that webinar, go ahead and take a look at it. It's pretty interesting. And the focus of that conversation was strategy, how organizations should think about AI adoption, governance, risk, accountability. Today, we continue that conversation, but from a different angle, right? The physical reality behind AI, the infrastructure, and the energy that is required to run it. And this topic came up after coming from today's guest that caught my attention immediately. And Clay is doing his PhD work focused on integrating data servers into microgrids. Like, holy crap. As AI platforms continue to grow, the energy demand behind those systems become real engineering challenge, especially for grid operators and microgrid environments. Clay Koplin is the CEO of Cordova Electric Cooperative in Alaska, where he works on one of the most advanced microgrid environments in the United States. His work combines energy systems, grid operations, emerging computing infrastructure. And it's that intersection what we want to explore today. So Clay, welcome to OT Insights. Great to have you here. Appreciate it.
Thank you. Good morning.
Perfect. So first question, Clay, let's start with the basics. To us is the basics, to you is like you've probably been doing this every day for the past few years. When you talk about integrating data servers into microgrids, what does that actually mean in practical terms?
Yeah, so thank you, Ed. We hear a lot about system integration, and it's a little amusing to me. In our microgrid environment, um, it's a very small electrical system. And so if we add a significant energy load to that system, we somehow have to maintain our power quality and make sure that large element on our grid interacts and plays well with the other devices. So I think of a grid almost as an organism, and you're adding new organs, new pieces to this living creature that is our electric grid, and it has to play well with the other elements of the grid to maintain again power quality and keep the lights on. So we have done a tremendous amount of system integration over the past few years. We have added hydroelectric power plants to our formerly all diesel power based grid. We've added battery energy storage system to our grid that we're actually using to balance the frequency and control the grid. We've added a system called an organic Rankine cycle that takes the excess heat from our diesel generator and produces
Wow.
additional electricity with it. Um, we've done a lot of work in the integration space, and these devices have to move handle load changes well, even if a diesel power plant is providing most of the energy to the system, and then it starts raining, and our hydro plant has the ability to start producing more. That has to be a very well coordinated handoff. We slowly increase the output of the hydro plant as we decrease the output of the diesel plant. So data servers are a very significant energy consumer.
Mm.
And as we look at actually providing electricity to a data server on our grid, we have to make sure that that's going to play nicely with our other equipment, not only to provide reliable and high quality power to the data server, but also so that the data server doesn't compromise the quality of the grid itself.
And this is a simple question. I'm trying to understand why why is there a need to integrate a data servers into the grid? Is it for like for data centers so that you can offer those services, or is it for your own use from intelligence perspective? What's the reason?
Yeah, so there's various reasons, socioeconomic and so forth, why electric utility would want to or not want to host a data server. From Cordova Electric's perspective, when I say that we're a remote microgrid, that means that we're a community-based grid, electrical grid here in Cordova. We are not electrically connected to other grids. So we
Okay.
have to operate our grid, our very small scale grid, the same way that the national grid is balanced. So we have limited opportunities to sell energy. We have limited opportunities for economic growth. We don't even have roads connecting our community to other communities in
Wow.
Alaska. So we are very isolated. It would be, we have significant excess hydropower available in the summer months, but we have no market to sell that to.
Okay.
We have a seafood industry that processes literally the highest quality salmon in the world, the Copper River salmon in the summer. But it would be prohibitively expensive to extend a transmission line. Even to Valdez, 80 miles away, we're talking on the order of hundreds of millions of dollars to have a transmission line to move fairly small amounts of energy back and forth. But if we can put a data factory in our community and use that energy to process data, we have fiber optic connection to Valdez,
Oh,
and we can export data services and have a home for our energy here. So we see the potential for a data server. It will be actually an anchor tenant in our community, be our most significant load. Now, this is micro scale. We're talking
yes.
hundreds of kilowatts, not hundreds of megawatts.
Right.
But the relative impact on our grid is the same impact that a hyperscale server of several hundred megawatts might have on a grid down in the
That's
lower 48 states.
okay. Perfect. Clear. All right. So now, now we're all aligned as the reason why, because that's going to be a question. Well, all these issues, why? So perfect. All
Yes.
right. So let's continue then the conversation. Now we have that understanding. Let's focus on AI. Most of the conversations around AI focuses on models, algorithms, and software. And from your perspective, how big of a factor then is the energy demand behind these systems? Because that's the part that we never think about, right? So,
Yes, you can't separate the two. Computing has always been energy intensive, and there's those trade-offs. The faster a processing chip, the more energy it's going to consume. There's some physical trade-offs there. So the more intensive computing you do, the more energy is required to process that computing. Not unlike a human, where the brain is actually one of the most energy consuming organs in the body, and the harder you think, the more calories you consume. So they're pretty much inextricable. Uh, you as you add compute, you have to have the energy available to meet those needs.
and so how do you calculate this stuff? Do you use models to calculate the requirements? How do you just go by the specs provided by an NVIDIA, for example, for their chips and however?
Yes, and I want to be clear, we haven't physically connected and started operating our data server
Okay.
yet. We do have some small cloud-based servers that have been installed. They don't have clients on them yet, other than the control system itself. So we don't have the physical experience of operating those devices yet, and that's some of the questions that I'm working on in my PhD research.
Yeah.
And I like empirical data. I like to touch and feel and see how something actually plays. Um, there's a lot of misconceptions about how energy actually works on a grid. And there's reasons for that. Structurally, the electric grids down in the United States, for example, you have several layers of ownership, and you have kind of silos in the overall holistic energy grid. So in other words, you might have a fuel gas storage vendor that has a part of the stack, and then you have a natural gas delivery pipeline system, and then you have a generation company that produces the power. You have a distribution utility that sells the power. So you have all these pieces of ownership stack, and you really don't get that holistic view from a customer's toaster all the way back to the power plant, of how it all fits and plays together. And frankly, it's very hard to coordinate and manage that. One of the unique things about Alaska is we're in a very low regulatory environment.
Okay.
We're not regulated by the Federal Energy Regulatory Commission because we're not connected to the national grid.
Oh,
So
okay.
there's no interstate commerce that happens over our power lines. So we have low levels of federal regulatory. And then as Cordova Electric is not even rate regulated by our own state as a cooperative, our customers. So um, getting a little long-winded here, but
No, it's
all that to say, we're completely vertically integrated. So I say that in a microgrid environment, if you throw a bowling ball into the Pacific Ocean, what are the impacts? Very hard to measure the influence of that bowling ball on the Pacific Ocean. But if you throw that bowling ball into a bathtub, you see every ripple. And that is our microgrid environment. And we have very high resolution sensors. So we throw a bowling ball into our bathtub, or we integrate a data server that can represent as much as 30 or 40% of our entire system load and can represent 20% of our annual sales. We are going to get very, very deep insights into how that system physically integrates and operates on our grid. So that's why Cordova makes a great case study, and that'll be the large element of my PhD on the front end here is what do we see and what do we know, and how does that stack up to our theoretical? To answer your question, devices are devices. I mean, when we connect a battery energy storage system, it's rated for 1 megawatt of output. It's going to fluctuate how much energy it's charging with or discharging to the grid. Then it's just a matter of managing that. And then as we very closely monitor how it works, we get insights. For example, we found out that the inverter on our battery energy storage system is actually inducing harmonic frequencies on our grid. So that
wow.
experience in integration advises our approach to data grid, and we want to protect against those eventualities. We want to make sure we're not introducing harmonics or voltage sags and sweeps. We don't power to backfeed from the data server's battery system onto our grid during an outage. So that's what we're mapping out as we
Wow.
start the integration process.
And that's part of your PhD. That's what you're focusing on. So you're at the leading edge. You cannot rely on everybody else to get those answers. So you're trying to find them yourself. Is that accurate
I
or similar?
so my background is a distribution engineer and working on microgrids, first at Kodiak Electric on Kodiak Island as a distribution engineer, and then here at Cordova Electric as the operations manager and ultimately the CEO. My expertise is in the microgrid space, and I would say high expertise. I engage nationally and internationally and have advised the U.S. Department of Energy on microgrid architectures, frameworks, finances. Um, the data side, I am very limited in my understanding. So that's where the bulk of my research is to improve my understanding of the physical attributes of data systems to better integrate the two. And I would love to take this opportunity to make a shameless plug to try to connect with folks in your audience that have that expertise in data infrastructure. I would really love to collaborate and have a value exchange between the insights that I have on microgrids and these edge compute environments in exchange for more insights into what the data industry needs and could become. Ultimately, we would love to have a data system that can actually integrate very closely with our energy grid. So, for example, as we have more excess hydropower available, the data system starts processing more data in response. Once you can co-optimize the availability of low-cost renewable energy with the operations of the data server, there's opportunities to ultimately reduce the cost of energy in our community environment and for the data
Wow.
server, and perhaps get the best value out of the data server. So
And that's interesting because, as AI platforms continue to scale and grow, right? They go hand in hand. They grow more energy because they need to suck in more energy. And you just mentioned you're finding ways to reduce. How do you help reducing that? So what are the challenges that the grid operators and in you microgrid environments face to support that kind of infrastructure?
Well, there's the physical challenges. As I said, we operate at a very small scale, but we have to provide all the same services as a very large grid that has a lot of distributed assets and a
Mhm.
lot of infrastructure. So we have to provide our own backup energy. You know,
Wow.
if an avalanche blocks the river and our hydro plant can't operate or gravel accumulates and we have to take the hydro out of service for a half an hour to flush the gravel out of the intake, we have to have significant diesel backup. So one of the challenges in a microgrid environment is that you tend to have a lot more generation capacity and a lot more backup and redundancy to assure reliable power in a very remote and very extreme environment where losing power, especially in Arctic Alaska,
Mm.
is actually life threatening.
Yeah.
So that all that additional excess capacity, though, is actually an asset for the data industry because that's what they need. They need energy capacity. So that's why there's an opportunity for a value exchange. We see the data industry as an opportunity more than a threat.
Wow.
But the challenges are to keep the frequency well regulated. So if you think of a large industrial load coming suddenly into service at almost the light speed that the electric grid operates at, your your power production equipment has to be able to respond to that. They have to be able to very quickly pick up that additional load
Mm.
without the voltage being compromised or even causing an outage, power outage to a portion of the grid. So we have to manage that. And then there's the economics of the remote environment, a small economy of scale on the relatively small amount of energy we sell from very large infrastructure investments. It's why our energy is very often, electric energy rates here are very often several multiples of the cost of energy on a large central power based grid with a large customer base. You know, for example, just our labor costs here are almost 50% of our cost of energy
Yeah. Wow.
because you have to have the expertise and the people to build, operate, maintain a fairly complex grid for 2,600 people. Um,
Wow.
so lots of challenges, but we also have opportunities, especially in Alaska. We have a very cold environment.
Mm.
One of the most energy intensive, many times the most energy intensive part of supporting a data server is the cooling. So our
Imagine
cloud
that.
server, yeah, yeah. So we have a lot of help from Mother Nature in that regard.
Yeah.
Um, so actually, when we collaborated with GrainSpark, the small edge data company, when they showed me their prototype, their pilot cloud servers, I said, "Well, you have this refrigeration system on in there. It uses a lot of energy. What if we located these servers inside our hydroelectric plant, literally 20 feet away from the generators that are producing the energy? So very electrically energy efficient. But then let's use the 40-degree Fahrenheit water right out of our water pipeline, a simple heat
Cool it
exchanger
off. Mm.
to cool it. And so they're approaching a PUE, an efficiency measure of 1.1, which is just almost unprecedented in the data industry. So economically, if our rates are 30 cents a kilowatt hour, but you only need to use a third as much energy because it's almost all going to data processing, we can compete with 10-cent power in a hot environment where they have tremendous cooling loads. So both challenges and opportunities, really.
Great. So going back to the how we started our conversation on LinkedIn right after the webinar with Marisa. Marisa was talking about AI being introduced into the OT environments, and you said, wait, AI has supported grid operations for decades. From an algorithm perspective, correct? Which is fixed, deterministic machine learning. So where do you see the boundary now from AI automation to the way that it was? Yeah.
That is a deep question. We could almost park this as a separate discussion and really dig into it, but I'll try to keep it simple. So you know, Cordova Electric has been a microgrid for over 100 years. We
Okay.
had a hydroelectric central power in 1907 to support a large copper mine, and at the time, the world's largest private railroad went 220 miles across the wilderness of Alaska to this copper mine.
Wow.
So we had telegraph wires, and so we have this long history. And up until about 20 years ago, the entire electric grid, we had ultimately switched to diesel generators. It was all manually operated. So operators walking around with a
Mm.
clipboard, measuring, looking, reading the gauges, making sure that engines weren't overheating. They'd have a checklist to make sure that they prelude the engine, then they turn on the thing, then they close the sync scope. It was 100% manually operated. And then because we were so far behind the rest of the industry, we were able to leap several generations of technology right up to a completely automated system. So as the industrial, programmable logic controller, computer platforms, the advent of very reliable sensors, good industrial software platforms, Wonderware integration, ignition, so forth. We automated our whole system. So I got to see both the human behavior change between a manually operated and an automated system, and we also had to puzzle out what do we want the operators still doing and not doing? What do we want the computers, in our automation system to handle? And again, in a very extreme environment where we can experience volcanic eruptions, earthquakes, avalanches, tsunamis, floods. There's a lot of dynamics in our external environment that influence our hydro plants, especially. So, probably best to give you an example, but I would just say there's a few kind of high level frameworks that we've puzzled out, and it's what I call the man machine interface. What do you want the operators to have custody of and control of and responsibility for? What do you want to have the automation system have control for, with the end goal of highest system reliability and power quality on an affordable and manageable platform? And it turns out that the what is maybe not as important as the when. It turns out that the operators, if they have to do very repeatable processes over and over and over, people quickly get bored, distracted, and ultimately we would get power outages because they get so used to entering the set point for where a hydro needle should be, for example, that even if they have to enter it twice, um, ultimately instead of entering a 5, they'll enter a 55. The valve will move too quickly and cause an outage. Well, in what I call blue sky conditions, the automation system will get that right every time. When you have the system programmed to see that the water level's rising, we have more water available, open the valve 1%. If the water keeps rising, open it some more. Eventually, when the water stabilizes to the level that we keep it at, then we're producing all the power that we can from the plant. And the diesel's in the background, just picking up the difference. So in what I call blue skies environments, the automation excels and humans perform very poorly. Um, but if you have operators that understand the physical plant because they build and operate and maintain it all the time, and you have very big weather dynamics, a huge rainstorm, we can get 15 or 20 inches of rain in a day, 24 hours. That kind of looks like a flash flood that picks up lots of trash and gravel and everything. Our automation system can't respond quickly enough to keep the trash screens from clogging everything. So in those events, we want the operator to be at the screen, at the HMI, operating the system manually, and it may come a point where the dynamics are too large, and we just decide that we're going to turn the hydro plant off until the storm runs its course. We'll stay on diesels and so forth. So, in degraded situations where you have threats or unexpected challenges, even a cyber event or
Mhm.
a degradation of your system, you want the operators at control, and that's where they excel. And it's where the automation falls flat.
And
So,
and that and that's interesting because again, that's the dynamics, right, between human decision and automated decision. Right now,
yes,
and that was a conversation with Marisa and also last week at S4, the human in the loop, right? When do
yes,
they come in? And when they take over automation, automation is great, but up to a certain
Yeah.
point.
Yes, exactly. No, automation has been an absolute godsend for us. It has improved the reliability of our grid. It
Okay.
has released the operators instead of having to maintain control the system and operate the system. Now they have the time to actually be out on the floor calibrating sensors, being proactive with our preventative maintenance, so forth. But just one little
Sure.
extension of the man-machine piece that gets a little closer to artificial intelligence, machine learning.
Mm.
We recognize that we have run-of-the-river hydroelectric projects. There's literally an inflatable rubber bladder, and we inflate that bladder. It creates a pond behind it in the river, and that water then flows through a pipeline. But any excess water just flows over the dam and on down the river. And so over time, sand and sticks and gravel accumulate in that intake structure. And periodically, we have to deflate the dam. We'll turn the diesels on and switch to diesel power for a half hour, 45 minutes.
Okay.
Deflate that dam, let all the gravel flush out of it, reinflate the dam, and turn the hydro back on. We realized we were following the same 10 or 12 steps to do that. And we thought, well, let's
Ah,
let's automate this.
yeah.
Why not? And so we did. We have a world-class system integrator that works full time for us now. He automated many power plants in Alaska and Pacific Islands and so forth. And but we still have optionality. So if we see that we're going to have calm weather through a 3-day weekend, the operators will leave the plant in auto flush. And they may come in on Monday morning and say, "Oh, look, flush the gravel on Saturday for a half hour,"
Great.
and that's great. Nobody gets called out. The automation performs beautifully. But if they see that maybe in July we're going to have the first big wet storm of the year, we know that as the river rises, it's going to collect sticks and leaves and gravel. The screen is going to clog very quickly. So they will leave the plant in manual. It won't be an auto flush, it'll be in manual.
Oh, okay.
So when the water level rises and this trash screens start to clog, the alarm goes to the operator. And the operator gets called out at maybe at 2 in the morning. He looks at his tablet. He manually operates the system and makes decisions. And then he may go through a flushing cycle. He may switch to diesel. And of course, we want to always optimize our hydro production. So
Good.
maybe I'll pause there.
Yeah, no, because
But
we only have less than 5 minutes now.
exactly.
But the last comment is once you enable automation, right? You focused on from a physical perspective, right? What could happen? But
Yes.
but once you open automation, now you got to start thinking from the cybersecurity perspective, what could happen? And I know 5 minutes is not enough, but how do you do it? Because again, when you were explaining the physical thing, it was almost like a black swan effect, right? What could happen if this? How do you deal that in the cybersecurity perspective?
Well, exactly. I mean, we see cybersecurity as just another unanticipated threat. There are risks, and those are things you kind of understand and can quantify, and they're probabilistic. But then there's uncertainties.
Mm.
Those are the things you don't anticipate. It's something that happens that you couldn't even have envisioned, that you never even contemplated. So cybersecurity is maybe somewhere in between. You know that you have a vulnerability, you have a program. If somebody can compromise that program, it can degrade your system. And this is where we worked with the national laboratories to
Okay.
to develop an architecture that segments those computers between our plants, so
Oh,
that if one's degraded, it will quickly air gap. And then we have backups of all our programming algorithms, even devices. It's so expensive for us to run a diesel, sometimes thousands of dollars an
mm.
hour, that we can afford to have a lot of. So we'll have a PLC that already has the current program loaded in it, sitting on a shelf, so we can swap those out very quickly. We have two data servers. If one goes down, it hot cuts over to the other data server for the master control program.
So your
So we have
resilience
layers
in
of,
place, yeah.
yeah, so we have various both architectures and responses and protocols to um, try to prevent a cyber intrusion, but also to recover if we do have
Yeah.
if the worst happens.
Yeah, resilience is extremely important, both in the digital and physical world. So,
Exactly.
Clay, it's been really, really amazing. All the, clarity and all the insights you're providing. Again, OT insights. So that's what we're looking for here. So really appreciate your time. Early morning for you, and we're recording this 6 a.m. your time. So really appreciate you waking up early, and thank you so much for being with us.
Absolutely. Yeah. Thank you for the conversation. I feel
Yeah.
like we just scratched the surface.
Oh, believe me.
Late career, after 30 years of this, we've developed a lot of insights and again, would love to partner with, even the largest among the data hyperscalers and so forth to help them understand the remote environment and the value, the access to energy they could have in those environments, but the value they could bring to those communities and those grids where they are much more welcome perhaps than in the hyperscale space, and frankly can very likely be the best playground for them to develop a more efficient and interactive architecture at that data processing energy interface in the future.
Perfect. Thank you so much, Clay. Everyone, thank you for your time. Hope you had enjoyed another episode of OT Insights. We'll see you next time. Thank you so much.
Thank you.